Hello, my name is Polina Bungina. I work as a senior software engineer at Zalando, a European e-commerce platform. But I'm also a co-maintainer of Patroni project, and today I want to share with you some insights about how it works, which might be helpful for everyone who is building or operating high availability for PostgreSQL. Okay, let's find this out. And the agenda for today is to look into what actually Patroni is in terms of functionality, what are the main functionality blocks, what it can do for you, and then look into the, of course, most important part, automatic failover. What are the common mistakes, what people usually do wrong in this sense, which will allow us to understand why Patroni looks like it looks like today. And then we will go deeper into Patroni itself. We'll look into the architecture, how it works, and quickly talk about the notable feature it has. So, what is Patroni? Um, this is important to say that it's originated from a Governor project by Compose Company back in 2015. And since then, the main functions of Patroni were, of course, automatic failover, but also creation of cluster for you at its initial setup. Cluster management, for example, you can centrally configure your Postgres instances. You can do some maintenance work as restarts, uh, something scheduled as a, again, restart or switch over. And also to some extent, you can get some important monitoring information for Postgres, for your instance. Of course, it's not the actual monitoring system, but some useful information can be gathered from the Patroni API. And now to the automatic failover itself. What are the common mistakes done when implementing such solution? Um, the very naive way of doing this, and the first thing that will come to your mind is, of course, to run two Postgres instances or any kind of number of Postgres instances, and just to ping primary from standbys with so-called health checks to see if it's still there. And if health check fails, for example, after some times, we will decide that primary is off, primary is down, and we probably need to promote the current standby and make it new primary. But there is an obvious problem here. If there's something with network, not the primary itself, we cannot differentiate this. And in this situation, we will just decide without actually knowing if we still have primary running or not. We will decide to promote our standby, which is of course not good. We will have the very worst situation for any DBA. We will have a split brain here when two primaries are running simultaneously. And this is obvious that we need some kind of backup way of making sure primary is remoted, or in other words, isolated from any writing load, any writing actions uh, before promoting the standby to a new primary. But this means that we need a secondary network, any kind of backup network, to perform this so-called stoneit, shoot the other node in the head operation to make sure primary is not running again, not accepting write connections and changes. But I would say it's quite difficult to do, almost impossible to get it right. And this way we can come up with the next solution, which is actually quite common nowadays, to have a witness node or arbiter, whatever you call it. But it's actually a node that pings or checks the current health status of primary and standby, or all of your Postgres nodes. And there is an obvious downside here, of course, that this is a single point of failure. And whenever you have your witness node down, you basically have your all HA down, high availability. But this is not only about this. Actually, there can be a so-called network partition where your primary is not accessible from the witness node, and another standby. It's basically isolated. And here we come to the very same problem. Witness cannot reach primary, cannot make sure that it's not running as primary, not accepting writes anymore, and just promotes standby on this information. And this is again a split brain. So to sum up, what we should consider when we are building auto failover solution. At least always think about network partition. This is the very important part. It can happen in many different ways actually, but you really need to consider this happening. Another thing is to think of the scenarios of split brain and how you prevent this. In other words, how you do fencing. The stone that I mentioned before, you can implement it in very many different ways actually. You can just shut the electricity down. You can reconfigure the proxy running in front of the Postgres that is redirecting the user queries to the current primary. So you just now start to point to another Postgres instance. And what is very important, kill the old connections. And this is how you isolate the old primary. But there is one but very big downside here, that you still can have some local connections which you are not influencing with this reconfiguration of proxy. This way, it seems that the best and the easiest way is to have something running locally and performing so-called self-fencing. And the third thing I have not mentioned yet, but also very important, your HA component itself, so your agent or your monitor, can have some problems. For example, there are bugs, there is some resource starvation. And in this situation, there should be an additional component that checks the health status of this your HA component. And once it notices something is wrong, it restarts the whole system to allow it to return to the healthy state. And this approach is called watchdog. So now we decided that the best way is to have local agents and some arbiter that decides who is the primary, while agents are deciding and making sure the old primary is demoted, isolated from the writing activity. But there's still one problem here. Let's think of a more sophisticated deployment scheme. For example, we have multiple data centers in cloud providers. You would think of availability zones. But in this setup, you always will end up in a situation where you have your witness node and arbiter running in the same data center with primary. And after this happens, there is also a possibility that this availability zone data center becomes isolated. It's not reachable from the outside, not reachable by the standbys, but inside, everything seems fine. Witness node can reach primary, it just cannot connect to standbys, but that's fine. We still have primary running from its perspective. But in fact, all the outside connections are not able, they have errors, they are not able to connect. And our system does not perform switchover, even though we still have two healthy Postgres instances running. So how to solve this problem? Seems that we need to perform a collective decision. We need to make a collective decision. In other words, we need some kind of distributed consensus algorithm. And you can implement this algorithm inside your agents and witness node, but of course, there's always a good reason. There is always a good idea that you can use something from the outside, so something already implemented. And most likely you already have such a system in your infrastructure. It can be Etsy, Console, Zookeeper, but they all implement this distributed consensus algorithm. And your agent can just make use of it. And now I think it starts to remind you something which is actually true. This is how Patroni works. Now to the actual topic, how Patroni works. And let's start with the general idea. The general idea, as I said, is to have something external that implements the distributed consensus. It can be either Raft, ZEP, whatever. But what are the systems that Patroni supports? It is etcd, Zookeeper, Console, Kubernetes control plane. They all fit this requirement, but other requirements are it should be a key value store for all the systems. I mean, the requirements are to be a key value store. They should perform and implement automatic compare and swap operations, atomic compare and swap operations, and implement some kind of expiration for the data, be it lease, session, TTL, as well as watches for this expiration, so that other members of the cluster can be notified that the data is expired. Let's look a bit deeper into how it works with this graph. So we have two Postgres instances running, and alongside we have Patronis. So the Patroni on primary, its job is to periodically update leader key and also write some other important information to the distributed configuration store DCS. Other members also write something. They write some important information about them to the DCS also periodically, and also they subscribe to the changes of the leader key when it expires. But update of the leader key means not just refreshing the value. It's a bit more sophisticated. As I said, it should be a compare and swap operation. So we only need to update the value if the previous value is the expected one. So we have our own name written there already. We also refresh the time to leave, TTL, to make sure the key is not expired. This way, as long as leader Patroni instance can update leader key, its Postgres instance keeps running as primary. But in any kind of situation where it fails to do so, it means that it is not able to be running as primary anymore. Let's look into the situation when, for example, the worst happened. We have a split of network. Our primary is isolated from other standbys and from the majority of the etcd nodes. For example, it can only access one etcd node, which, because it cannot form the quorum, becomes read-only. This way, primary can only read information from DCS, but not write into it. After some retries, it understands that it's not possible anymore, and what it should do, it should demote its local Postgres. Patroni demotes local Postgres once it understands that it cannot update leader key. At this point of time, TTL is still valid. Our key is still A, the name of the primary node, but the primary is already demoted. After some time, the key will expire. And as I said, standby instance of Patroni will be notified that leader key expired. As you see, it happened already after the old primary is expired. So we are not getting the split brain situation. After leader key expired and standby node is notified about that, it attempts to create leader key with its own name, and if it succeeds, it promotes the local Postgres instance. When I say create, it's not just like simple create. It's actually, again, a compare and swap operation, because we can have a situation where there is not only one but multiple standby nodes, and they all will attempt to do those situations of creation if they're eligible to do so. And the compare and swap is about checking if the current leader is not present anymore, and we can create key with our name, like make us primary. And the one who leads will become the actual primary because the writes are serializable in etcd or in other systems that we use, and one of them will succeed, but all others will of course fail because the condition previously existing uh, is not right anymore. We already have one created. In this case, node B became a leader. Its Patroni promoted the primary. Others failed and continued to write as standbys. Now let's look a bit into what is actually written to the DCS. As I said, we don't only leader doesn't only write to the leader key. It stores quite some information about cluster. Yeah, so we have configuration stored there. This is a global configuration that is applied to all the instances in Patroni cluster. We also have a unique identifier of the cluster stored there. The most important, as I said, leader key, and so-called members key subdirectory that contains all the keys for members, which can serve as a service discovery because it contains information about the members important for connecting, for example. I will show this a bit later. And other keys that are not in bold here, they are stored in different times, but yeah, this is the ultimate list of everything that can be written to the PCS. If you are a user of Patroni, you definitely saw this table and used Patroni CTL utility. And this table represents the current state of Patroni cluster. And actually, this information is retrieved from DCS. Let's look a bit deeper into what is retrieved from where. Again, leader key is the name of the node of the member running as a leader. Initialize key is the unique identifier of the cluster. We also have information about any member in the cluster. And as I said, it can serve as a service discovery because it contains connection URL, API URL, current wall position of this member, etc. And another very important key is status. It's written by leader as well. It stores there its current wall flush LSN, information about the positions of all the so-called permanent slots Patroni maintains, physical and also logical ones, and our latest feature implemented in Patroni, retain slots list. It's the list of the member slots which Patroni creates that Patroni must maintain for a specified period of time after member disappears from the cluster. So the slot stays and it keeps walls for some time, allowing the member to return to the cluster and keep streaming from the primary. This might come in handy for those who are not using continuous archiving, or it also helps to maintain your logical slots in a valid state. Yeah, and this is the very short version of how Patroni works. Now let's also look into what are the cool features, the bigger features we have. Yeah, what really makes it so cool. I would name 5 of them. Of course, we have much more, but those are the bigger ones implemented in the past years. We have a standby cluster feature, which allows you to run cascading replication in a remote data center or region. We at Zalando use this feature a bit differently. We set up cascading replication for running heavy and long-run analytical queries without disturbing the original cluster because we are restoring it from archive only. We also provide synchronous mode, which makes Patroni operate synchronous standby names. depending on the currently available healthy standbys and their positions. One step forward is a quorum-based failover feature. Um, it allows to make use of the quorum commit feature in Postgres. Another, and probably my favorite one, is the DCS failsafe mode, which allows you to keep running the whole cluster in write mode. So do not demote primary if DCS is out for some time. This is, as I said, when the primary Patroni cannot update leader key, it of course means that it will demote the primary Postgres to the standby, but this is probably not what we want, and this feature allows you in certain situations to avoid this. If especially it's very useful in Kubernetes, where we know that Kubernetes API can blink or go away for a couple of minutes, for example. And last but not least, Patroni supports Cytos extension and allows you to build highly available Postgres clusters. So, yeah, the last slide will probably be about the links I consider the most useful for all our users. These are the talks and tutorials about, even podcasts about Patroni, how it works, may give you more information because they're a bit longer. And the three last ones probably are must visit. Documentation, please read the documentation. A lot of questions go away if you carefully read one. Change log, please monitor change log of Patroni to make sure you see new features, but also you are informed whether your bug is fixed before reporting it. And for reporting bugs and asking questions, we have a Slack channel in Postgres Slack. Yeah, this was pretty much it. I really hope it was useful for you, and I will be happy to answer your questions.